There are two different versions of answers to this question. The easier one would be you are just trying to find a line with the same slope as this function and goes through the same point as this function. So you use that as approximation. So suppose you have this orange line here, and you center it around a point, and you want to find a line that goes through this point and has the same slope. So the way to do this, if you are given the slope m, and you are given a point, then the line is y minus b equals to mx minus a, which you should know how to do that. And so if you apply it to this particular equation here, and you rearrange it, you get y is equal to fa plus f prime a x minus a. And fx is, this line is approximately equal to y around that point. So the technical, which is the correct definition, the correct version of this is, suppose you have any infinitely differentiable function, it can always be written as the sum like this. So the original term plus derivative multiplied by the difference plus the second derivative divided by 2 multiplied by the difference squared plus third derivative divided by 6 multiplied by the difference cubed. So in general, if you want to have an infinite sum, then this notation means the nth derivative. So f nth derivative evaluated at this point divided by n factorial. This thing is n factorial, which means n minus 1, n minus 2, and so on until you multiply it to 1, and multiply by this difference to the power n. And if you sum them from 0 to infinity, it's equal to this original function. So remember, here it's equal, it's not approximately equal. So we call this kind of thing the Taylor expansion. So after we have the Taylor expansion, and if we assume x is close to a, then this x minus a term is very small. So if f minus a is very small, then if you go back up here, x minus a squared will be even smaller. So this term is approximately 0. And similarly, x minus a cubed will be even smaller, so it's approximately 0 as well. So everything other than the first two terms goes to 0 as x gets closer to a. So that's why fx is approximately only the first two terms, which is fa, f prime a multiplied by x minus a. So two examples would be, so suppose you have 1 over 1 minus x. If x is smaller than 1, then you have a Taylor expansion like this. So it's just x to the power n and sum it. And similarly, if you have e to the power x, you would have a Taylor expansion like this, which in general I think is x to the power n factorial, and you sum from I think 1 or 0 to infinity is okay. And this is true for any x. So an approximation, suppose x is very close to 0, then all these things are very close to 0, so you have a linear approximation for e to the x. And similarly, for sine, if you do the Taylor expansion, if you actually take the nth derivative and figure out the coefficients, then you actually know that it's this is harder to write like that. So if n is, there is a minus 1 to the power n here. So what I should say is if n is odd, so you sum up only the odd term, and that gets you sine. And in fact, in your calculator actually does not know how to compute sine. So it uses the first, the 10 or 12 terms to approximate it. And the approximation would be accurate enough so that you won't notice the difference up to 10 digits. So if you are just using a linear approximation, again, then all these things are 0, so you're only left with x. So sine x is approximately equal to x when x is close to 0. And if you want to represent this in a diagram, then if you have the original function as this thing, then the first order approximation is the dotted line here. So if you have a line like this, then it's basically a linear approximation. If you want to use the second order approximation, then it's a quadratic. So it might be something like this. So if you want to increase the degree of approximation, you can increase it to a third degree polynomial, which would look something like this. It's just getting closer and closer to the original function, and as the degree goes to infinity, it's actually equal to that function. But since I think you didn't learn Taylor approximation yet, so I will not go into the details. But again, as I said, when x is close to this point, so if x is in this small range, all these things are approximately, all the higher order polynomials like this are approximately 0. So you are only left with the linear approximation. So, and that's why we call it the linear approximation.